Hi, welcome everyone to this webinar. It's really a pleasure for me to be hosting this webinar today because, well, it's kind of a closure of a more than 3 years journey with this project. So it's really, really cool that we ended up all together here telling you about what we have done and how cool this project was and is. So I hope that you can see my screen. Anything, just shout out. I'm Araceli Venegas Gomez. I'm the founder and CEO of QEC. We really focus on education, training, skills, and anything that has to do with awareness and trying to connect people. And here we are connecting you with this project. This project was funded by Innovate UK. We started in February 2022. We were just talking about how time flies, and we are here to tell you more about what we have done and about the project. So today, we are going to be hearing different talks, four short talks for you, where you're going to be learning about a lot of different things. You're going to learn about quantum error correction from the hardware perspective based on trapped ion quantum computers. Mark Webber will be our first speaker, and he will tell you more about what Universal Quantum is developing. Then we will have Christoph Sunderhauf, and he will work more on, he's working more on the software side and the algorithm side for quantum error correction, and he works at Riverlane. Then we will have David Galvin from STFC telling more about the quantum research perspective about the project and what they have been doing. And then we will end up with the end user perspective. Leigh Lapworth from Rolls-Royce will tell us more about what they are doing within the project and in general. So really interesting discussions today. You are going to be hearing all the different talks. You can ask your question anytime in the chat. You will see that in the right-hand side, you have the chat and the Q&A. So just post your question anytime, but we will leave the Q&A at the end of all the 4 talks, okay? So everyone will come on stage at the same time. What is the QEC project, Quantum Error Correction Project? It's really a unique project where we have, as you have seen, the hardware side, the software side, and the application side. How to think about an end-to-end solution for quantum computing, from developing the hardware to developing the software that connects the hardware for error correction, to develop the software for an application, a very specific use case solution, and how everything will be thinking then on the long term for users, for how this is going to be a new solution that is going to be available in the market. This is unique to this project. So we have 3 very technical challenges here. Obviously, the first one, the hardware side. And the different partners within this project have been working on developing a unique solution based on ion trap, and Mark will tell you more about that. Then you have the technical challenge on the software for error correction. We are looking here about the long-term solution for quantum computing, no errors. So full-term quantum computing, as you probably know, is very hard to achieve. So how to look at the software that can really tell us that there are no errors on our hardware. And then you have the technical challenge on how to apply this for specific solution. What is the business side of it? How could you think about selling this to different end users? What is the end user really expecting from this solution? So we look at this holistic perspective as an end-to-end solution for quantum computing and the use case for computational fluid dynamics. And you will hear more from Leigh on how they have been applying this for Rolls-Royce. I think without further ado, the only thing that I can tell you is, well, this has been the consortium for this project. Fantastic work during these 3 years, and we are closing at the end of this month. But we really think that it's the beginning of hopefully a very long journey for quantum computing, being full-term quantum computing a reality in the coming years. So without further ado, I'm going to end up my talk, and I'm going to let the stage to Mark. Welcome.
Yeah, hi everyone. Hello. Sorry, just one moment as I share my screen. Okay, I assume you can all see that. Hi everyone. So yeah, I'm Mark Webber. I'm the quantum architect lead at Universal Quantum. I spend a lot of time working on both error correction and applications for quantum computing. And the work that I'll be showing today is a collaboration. We're working closely with Riverlane on the aspects of quantum error correction. And what I would like to do at the very beginning is just to very briefly introduce the quantum hardware approach of Universal Quantum. So on the hardware side, we are building trapped ion quantum computers. We are very focused on scalability. So quantum computers exist, you can use them today on the cloud, but the issue is the number of qubits that are available. These quantum computers are not yet outperforming super classical computers. What we need to do is increase the scale. We need to go to larger number of qubits. Maybe we're at 100 today, we need to go to 100,000 perhaps or more for the most impactful quantum advantages. And to do that, we need the underlying hardware to be scalable. So the hardware we build is individual trapped ions, so atoms, they're charged, they're an ion, they're trapped within electric fields. And the image that we can see on the screen, we build these microchips, and the ions themselves float a number of micrometers above the surface of that chip. And we're able to move them around. We can physically shuttle these ions around and enable connectivity. The scalable piece comes from how we're able to connect our modules together. And that is very much to do with what we're seeing here. It's a big challenge to connect separate quantum modules together. Those connections need to be quantum in nature. And when you separate these modules, say they're in their own vacuum system, it's a really big issue. How do you get quantum information between separate modules? What I would say then is what we're approaching in the way that we're tackling this problem is very different. It's something we've demonstrated, and it's the connection between modules that is itself mediated through ion shuttling. So we're looking at here two separate modules, very minor gap between them. And by precisely aligning these modules together, what we're able to do is physically shuttle one ion from one module to another. And the quality and the rate of this operation, as demonstrated, is extremely superior to the alternatives. And it leans into our vision for a large-scale device in that individual modules can be fabricated. These are produced in similar ways to mature silicon fabrication techniques of normal microchips. There's additional layers, of course. But the large-scale device then is achieved by producing these individual modules that are then tiled together to create one large plane where an individual ion or atom can be moved from one module to a very distant module just through physical shuttling. So that's a brief introduction to the hardware. And in terms of what we've been building as part of this project, we have spent a lot of time creating a very accurate and realistic emulator for the hardware that we are building. So when we do our investigations, we're interested in quantum circuits. These circuits, like in classical computing, are a number of operations, logical gates. In classical, you have AND or NOR gates and so on. But the gates within quantum are slightly different. But we still have this circuit, as we call it, a list of operations between qubits, quantum bits. And our emulator then takes that arbitrary circuit as input. And the flow of this project was in collaboration with Riverlane, where they were developing circuits for quantum error correction protocols. Quantum error correction is this way in which we combine many low quality qubits and they collaborate in such a way to produce one high quality qubit. So we want quantum error correction, and this was a tool that we used to understand what would the best error correction protocol be for our hardware in particular. And the strength of our hardware is in the long range connectivity. We can move our qubits with high fidelity, high rate in such a way that allows us to connect those distant qubits. So the flow of our emulator is this connection between an input circuit by an end user, in this case, Riverlane, doing investigations, and that circuit is then consumed by a realistic hardware compiler. Of course, when we take this arbitrary circuit, there's no notion of ions whatsoever. It's targeted on qubits. What we need is our hardware compiler that now translates that arbitrary circuit into machine instructions that relate to the physical movement and orchestration and laser and microwave-based gates for ion specifically. So the hardware compiler connected in this flow is the hardware compiler for our near-term hardware. And it's this connection that then allows us to learn really relevant information about how well this circuit will perform, like how long did it take to do ion routing, or how much error you might expect due to the scheduling of various operations. So in this flow, we continue. Once we've compiled, we can consume that rich information involving timing and other aspects to then insert into our arbitrary circuit what we call a circuit error model. This captures things like the infidelity of gates. Every time we do a logical operation, it's imperfect. There's a certain error associated with it. We insert that into our circuit, including consuming the timing information, which is related to coherence time, to then have a circuit that is the original circuit, but now with error terms inserted into it, very much motivated by the hardware understanding and the specific compilation of that circuit. And then finally, that circuit that we have ready with errors is able to be simulated. And there's many ways to simulate qubits with different pros and cons. If you want a full quantum state simulation, then the limits of qubit numbers that you can reach is rather limited. However, there are techniques to simulate much more efficiently as long as we restrict the type of circuit that we're looking at. And it turns out that that is quite applicable to quantum error correction protocols. So we simulate that circuit that Riverlane has provided with all that rich information and then feed it back to them so they can know how well that logical or quantum error correction protocol that they put together has performed. So this is the core of the project as it related to quantum error correction research. And now to jump to some results from Riverlane. And I won't spend too long on this. I know I don't have a huge amount of time, but the message from this is that we're comparing different error correction protocols, the surface code, the toric code, different error correction codes with different strengths and weaknesses. But in this case, in green, the toric code is an error correction code that relies on that long-range connectivity. To do that circuit, we need to connect distant qubits, which is a strength of our hardware. In contrast, in red, the surface code is only nearest neighbor. Only the qubits that are locally adjacent to one another require any operations between them. And through using our emulator, we find that given the assumptions on the hardware, that code that requires a long-range connectivity does outperform the local code. And that's only the case based on, well, what are the assumptions on how well we can do connectivity? So it's this flow that's been very helpful to really understand, is our hardware where it needs to be to perform the types of codes that we hope to be able to perform that relate to the sort of connectivity within those error correction codes. And then the final point, and this is very much connected to the computational fluid dynamics research of both Riverlane and Rolls-Royce and others, where there's been a lot of research on, well, we're going to run this problem, but the algorithm, like what algorithm are we going to use? That a lot of research has been done now as part of this project, and you'll hear more. But what we have done is taken the algorithmic details, the number of logical qubits, the number of gates, and passed that through a resource estimation process that includes the overhead of error correction and lots of details that go into that error correction process, along with the hardware assumptions of fidelities and operation rate, to then show the number of physical qubits and the resulting runtime to run this large-scale application. And we're talking about large scale here. We're talking about 100,000 qubits or more. So this is a combination now of the understanding from the error correction that we have built in this project, combined with the more hardware agnostic work on the algorithm side, brought together to then show what will we need from the hardware to one day provide an advantage. So I'll wrap it up there. I think I'm about on time and pass over to the next speaker.
Hello, everybody. Thank you for dialing into this webinar today. Mark has told you a lot about the error correction side and also the hardware that they have been developing. And here I will be focusing more on the quantum algorithms that we have used as part of this project, especially related to data processing. So the application area that we considered in this project was computational fluid dynamics. And the hope is that in the future, when you design a jet engine, for example, you can perform these computations faster than now. And in these computational fluid dynamics computations, one bottleneck is that you have to solve linear systems again and again and again and again and again. And this can be very difficult because the dimensions of the matrices, the dimensions of the linear systems can be very large. So the idea is to offload this to a quantum processing unit. This has been studied, and there's a timeline actually of quantum matrix inversion algorithm because there have been improvements. So the first algorithm to this end was in 2009, called the HHL algorithm, which started this entire field of studying linear algebra and linear systems on quantum computers. But then in subsequent years, there have been improvements, culminating in the quantum singular value transformation, which allows you to do linear systems and also do a lot of other quantum algorithms. And there has been an improvement in the complexity of these algorithms. So HHL has this complexity here of a kappa squared over epsilon. So epsilon is the accuracy of the inverted matrix, the accuracy of the solution that you want. And kappa is a property of the matrix you want to invert, the condition number. And this has improved a lot because in QSVT, this query complexity is only kappa times log kappa over epsilon. So it grows much, much more slowly with epsilon and also with kappa. And there is a hope that these will be able to be faster than classical solvers because of the dependence on the dimension of the matrix. So let me be a bit more specific and show you the circuit that we considered for QSVT. So what does the quantum circuit look like? This is a short example circuit here. And you see some rotation gates with some angles here. And these rotation angles that we have to use in these rotation gates, these can be pre-computed classically. Then we also have these U gates here, which are in between the rotation gates and these C0 gates. And the U gates, these are block encodings, so-called block encodings, which describe the matrix A that we want to invert. So the matrix A we want to invert is potentially not unitary, so we can't just implement it as a quantum gate because in quantum physics, everything is unitary and invertible before you perform measurements. But instead, we can encode it as a block of a unitary matrix. So here the U is a unitary matrix where the top left block is our target matrix A, scaled down by some normalization. And the rest is just junk, which only serves to be able to encode this in a unitary and put it onto a quantum computer. Now, you must choose the junk for the circuit for the U to be efficient. And the circuit here, you see it's very regular. It has here 3 repetitions that I put. But in fact, you will need more repetitions. And that's where this query complexity you saw on the previous slide comes in, because you need this kappa log kappa over epsilon iterations of this thing. So you need multiple repetitions. Okay, and that was the query headline complexity, the headline query complexity that you saw on the last slide. But if you look more closely into what each step entails, you will see that each step includes a call to the circuit for U. So when you want to figure out the actual total length in gates, you don't just have to look at this query complexity, which is the kappa log kappa over epsilon, but you also have to look at the gate count of U. And this is why you need an efficient circuit for U. And that's the difference between the query complexity. Quantum algorithms are often expressed in a query complexity to some oracle. In this case, the oracle is the U. And this is kind of akin to counting how many function calls you have to a certain function. That's the kappa log kappa over epsilon here. But then the actual gate complexity, so the number of gates that you have to execute on your quantum computer, if you want to figure out that, you have to multiply this query complexity by the number of gates in your unitary. And this is why you really need an efficient circuit for your matrix that you want to invert. In fact, I tried to make a meme for this, where I liken quantum speedup to an ancient Greek superhero, Achilles, because it's so powerful. But then if real-world applications come along, this means you will have to load data, and you will have your matrix A, which comes from your practical application that you are trying to solve. And that's kind of like an arrow, because if you're not careful, or if you're unlucky, your data loading can actually get rid of your quantum advantage, and you won't have any quantum speedup left. And because of this, it is important to study how you can block encode matrices and put them onto a quantum computer most efficiently. And to this end, this is a research paper, which we did as part of this project, of this QEC project. And here we figured out how to do these block encoding circuits more efficiently for some matrices by harnessing structure. So here's a simple example. This is just a tuplets matrix. And the point here is that it has many zeros in the top right and the bottom left. And also many elements are the same, like across all of these diagonals here. They're all identical. So all of these A0s are the same value, and all of these AD-1s are the same value. And if you create a block encoding circuit and you treat this naively as one dense matrix with just random values that you have to load onto the quantum computer, then your circuit would be n squared, where n is the dimension of the matrix. However, when you take into account the structure and exploit the structure, which in this case here, it's the sparsity and the repetition pattern, because you have so many repetitions of identical elements, then you can get a much shorter circuit, which only scales like d, which is the number of distinct elements, plus, in this case, log n, which is much better than n squared. And then this paper gives you kind of a recipe that you can follow to try to create an efficient block encoding for any kind of structure you have, any kind of structured matrix that you have. I just want to take one small step back and show you that this data loading is nothing specific to QSVT, but is a general issue in quantum algorithms. I think many of you will have heard about the Grover algorithm, which is often described that it allows unstructured search in a database of n entries in time square root n, which is a square root n speedup, because if you have a list of size n, classically, to find an entry, you go through it one by one, so it's time n. So I got the circuit here from Wikipedia, actually. And you see it says, yeah, you repeat this thing square root of n times. Then you have to look closer into the circuit, and you see this u omega here. So this describes the haystack. It describes the database in which you're looking for your needle. And again, we have this difference between the query complexity, which is O of square root n, and the gate complexity, if you take the implementation of this u omega into account. And in fact, if this u omega consists of a quantum circuit loading a classical list with n gates, then there is no quantum speedup, because you have square root of n queries to this u omega, which takes n gates. So we have square root n times n total gates. So this shows you that when using a quantum algorithm, you really have to pay a lot of attention to the data input, because otherwise your data loading can annihilate your quantum speedup. And likewise, you also have to pay a lot of attention to the data readout. So these are two factors you really have to consider if you want to retain a quantum speedup of the quantum algorithms. That's everything. And if you have any questions, we have the Q&A later. Thank you.
Okay, good. So hi, my name's David. I work as a quantum software engineer in the Hartree Center, part of STFC. If you haven't heard of us, we are basically help into UK businesses and academic groups sort of enhance their performance using HPC. So I'm going to present now something that follows on a bit about this idea of data loading. If I can get my slides to work. So this idea of state preparation and measurement. So we saw before this idea of data loading being able to undermine your quantum algorithm. So you could start off with, say, this idea of a linear solver. You have your right-hand side of your linear solver. You want to load this data before you input it into some sort of quantum linear equation solver. Even considering having to normalize the data and load your matrix, typically we approach this idea with the idea of amplitude encoding. So obviously the real value data is actually put inside the circuit through encoding it within the amplitude of the quantum state. Now, this turns out to be a very non-trivial thing to do in general. If you think about this idea, like, oh yeah, we have a unitary, we can simply put a unitary to load the data. But because of the nature of the way devices actually work, a generic unitary is not just a simple case of put the unitary there and then we're happy and we can just plug in the algorithm. We actually do need to decompose this into a set of gates, typically native instructions on the hardware. In the most general case, even without considering things like decoherence, we have this notion of a sort of exponential explosion in the number of gates that need to be used to create a generic state on the quantum circuit. So the question then becomes, can we leverage information from our domain to not have to do this? Now, it's very common in literature to look at things like ground state preparation, and there's a lot of stuff like that, but we're considering something that's more of a generic problem. So we have this idea of an amplitude encoding into a circuit with measurement at the end. Then we also have the idea of doing measurement so that we have to run our circuit so many times to reconstruct our state. So typically, if you're looking at the linear solver case, for example, we have to do a full state tomography if we actually want to get the exact solution, because we don't actually have access to the amplitudes themselves when we measure the output of a quantum circuit. We just have to sort of reconstruct this by many queries many times. So if we consider this case now of doing this as part of an iteration, for example, we do this idea of computing our linear solver using a quantum circuit. We do our state preparation so many times. We do our quantum linear equation solver so many times, and we make the measurements. So this approximated state, it goes back into our classical loop, and this reloads the data back into the quantum circuit. So the question then becomes, do we actually need all this data to be exact? Can we do approximations so that we have the same qualitative solutions without needing all the complexity? So it's a bit of a hard problem. The first thing that I looked at, I guess, was probably this idea of a tensor network approach. So tensor networks are sort of this idea, this graph representation of things, where you have these nodes and these legs or edges, and they connect to each other through summations. So each leg on each node, here represented by the green boxes, that are the nodes, and the legs, the red lines. So each one represents an index of the tensor. And when they're connected, that represents a summation over it. So obviously the two nodes have to have a compatible dimension, which is known as the bond dimension. So a particular case that's very famous, I suppose, is the matrix product state. So thinking then becomes, can we approximate our generic state in such a way that it looks like a matrix product state? Now, it's not necessarily simple to simply look at a state and say, yeah, here's a matrix product state for it. But there are some literature out there that suggests that if you have functional information about your state, that you can sort of create your matrix product state and then transform this into a circuit. So we have, for example, on the left side, we just have, say, we have some real data points, and we've done some polynomial interpolation of this. So we say it fits some polynomial function. Now, in reality, we wouldn't have such a nice fit, but we're hoping that an approximation will be just as good. So we can turn this into a matrix product state, and then we can turn this matrix product state representation of a circuit as something that can be prepared on the quantum circuit. So there is work by Shiju Ran. He talks about this idea of basically converting your MPS into a series of layered 2-qubit tensors or gates. So you start off with one layer with an approximation by cutting down your bond dimension to 2. And then you disentangle this from the rest of your circuit and do the same thing again and again. Now, with the generic data using a polynomial approximation, you can get up to about 90% fidelity with just 2 layers for only about 5 qubits. But it's still, I mean, it's not great. It goes in the right direction. So another approach you might see, so you want to, say, limit the actual depth of your circuit a priori, you could try this sort of ansatz approach. So you could model your circuit as a tensor network and try to do some sort of optimization of it in that way. So you have, over here at the left side, you have 3 layers of an ansatz circuit, very generically shown, there's no parameters given. On the right side, you have the MPS. Now, if you represent this as a tensor network, you can sort of compute this as a fidelity. So you want to optimize your fidelity. Now, doing an optimization by itself isn't simple. There's a lot of, I suppose, hyperparameters to consider. For example, you could probably do rotation gates, which have numerical values, and you could try to do optimization over that in Euclidean space. But you risk this idea of the so-called barren plateaus, where you have this sort of flat case where if you're trying to do your optimization, you simply can't make any progress. You may end up at one of these plateaus at a very high value of infidelity. So your state's not actually doing anything that's very good. Same time, your ansatz can only express so much, so it only explores a certain part of Hilbert space during your optimization. So you need to, in some way, ensure, or hopefully ensure, that you have this state that you want to prepare close or nearby the ansatz exploration space. So there has been work by Galvin, where they explored the idea of doing this sort of Riemannian optimization. So you're not doing the numerical optimization, you're doing this Riemannian optimization over the circuit elements themselves. So instead of doing this like parameterized rotation gate simply, you have this idea of actually moving over the unitaries. So it's we did try this out. It worked okay, but there's still work to be done. Now, there's also simply the idea, can you approximate your state by simply grouping the values, which is a very naive way. You would expect this still to be exponential, but you might find that in the actual prefactor that you're doing, in your particular case, it's simple. So on the left side, we have the idea of simply bucketing the interval in some way. We have this points that are laid out over the interval. Remember, this is a normalized state. So you just take the average of, say, a set of points inside a bin, and put them together. Or on the right side, you might do some sort of radial smoothing, where you do a pass over the state and say values that are very close together under a certain tolerance are treated as being essentially the same. The idea being that if you can do this, maybe heuristics will capture that fact and say do fewer rotations or do fewer C-naughts where it doesn't have to. So there is now the case of measurement. So you have this idea of we need to measure something and do full tomography. Well, what if we use a swap test? A swap test allows us to basically target the certain basis states and measure over those. So the generic swap test, you calculate the fidelity. You have this idea of 2 states that are already prepared, and you do a sort of a controlled swap, and then you do a measurement on your ancillary qubit, and this gives you the probability as well over several runs, which will allow you to calculate the fidelity to 2 states. So if we apply this to for example, a quantum algorithm, we have an output state X, and we have some basis state J, here represented by an X, just some set of X's to flip those bits into the computational basis you want. And then we can measure particular overlaps. Now, considering this, we could think about, hey, what if we only want to measure a certain number of bases? Well, what if we can transform the information that we got into a different domain so that when we measure over a basis, we're actually getting a lot more information that we would normally get. So this idea is like, for example, we do a Fourier transform on our output, so we transform it to Fourier space. Well, then we can do something like this, where we just do a swap test, and we now have a Fourier mode. Now, in this part, we have the magnitude of Fourier mode with a bit of, so it's jury rigging. You can also get the phase information as well. This allows you to calculate sort of a limited Fourier approximation in the classical sense. So you've collected a couple of Fourier modes, and you hope or design your circuit in such a way, or your plan in such a way, that you can simply get the state back by doing a few of these. Now, it's also appropriate to mention some machine learning approaches. So there's some stuff done, this idea of Clifford circuits, or I suppose where you do classical shadows, where you do this easily simulable, relatively speaking, Clifford circuit at the end of your circuit, and then you do your measurement, and then you do the inverse of this to produce a classical shadow. Now, machine learning algorithms have been proposed to actually use this to do state tomography. So it looks something like this. Now, here's an example of how it might look. So we use the Atos QLM that we have access to do this for generic state. So you have this, the infidelity training goes down further and further using a very simple neural network. It's like the most basic out of the box one you can use. And you see the infidelity, it gets to a low value, but it's not quite low enough. But this is very, very naive. So that with further refinement, you could probably see it preparing something better. Now, if you are actually leveraging the information application domain, you may be able to make further refinements to your neural network so that when it actually does tomography, it looks good. So we see here, for example, we train on the target states. Some cases, the infidelities are okay. Some of the states these are considered to be nearby states. In other cases, they're pretty widely off. That's just the nature of this. It's a very naive neural network model. You can see now, though, there's a lot of circuit runs being done here. So there is a lot of refinement to be done in this way. Now, when it comes to the swap test, we have also the idea of approximating our Fourier modes. So on the left side, you see this ratio of our approximation relative to the actual value. And we see that obviously with more shots, we get closer and closer convergence to the end of it. So I suppose that was a bit of a gallop. But this is really just to point at future directions you can take this. So the problem of actually state loading things is not solved. There's a lot of work to be done. There's a lot of interest being generated. The main takeaway is, how do we actually use information in our domain of application to reduce this generic overhead? Yeah.
Okay, good afternoon. I was expecting my presentation to start. Let's try again. There we go. Okay, so I'm Leigh Lapworth. I lead quantum computing at Rolls-Royce. Not sure whether that is a bit dark, my screen. Yeah, let's try. Can we move on? So start by saying a little bit about computational fluid dynamics, because I'm not sure everybody knows what that is or is active in the field. It's a way of doing simulation, and it's representative of lots of different types of simulation. But in practice, we want to design something, a gas turbine in our case. So in this case, we want to design that little component that's circled at the top there. It's part of the infrastructure that holds the engine to the wing. So we put a mesh on that, and in many cases we use a simple lattice mesh. So we come down and create that mesh. We've got the Navier-Stokes equations there. They're pretty universal, model all sorts of flows, and they basically represent conservation of mass, momentum, and energy. So we discretize those and we put them on the computer. We run the computer, we get the answer, which is the bottom right, and that's contours of pressure. That allows us to check how good our design is, and we then say, okay, that's not good enough, we'll make some changes. Sometimes that involves a designer making choices about how to change the geometry. Other times it's wrapped up inside an optimizer, and we just let the optimizer repeat those whole loops. So let me move on. So we've discussed this a little bit already about the fact that quantum mechanics is a linear theory, and in many cases, as is shown here, we've got a nonlinear set of equations we want to solve, but we basically make an approximation, make an initial guess, discretize or linearize about that initial guess, and discretize. That creates essentially a large sparse matrix set of equations to solve. We solve those as a linear system. We update our model and then check whether we've converged, and I'll show a little bit about convergence later. If we haven't, we've now got a new guess. We go back around that loop and keep going until we reach convergence, and then we stop and save our solution. Now, this logical model of taking a solver and then taking something on a CPU and then running on something else to do the solution, quite generic. You know, we could have drawn this with GPUs. This one is for quantum computers. And we then have there's two extra layers. So the first is the interface. We have to interface between the classical computer and the quantum computer, which in general we would call pre-processing and post-processing. So we pre-process the model to then put it on the quantum computer. And one of the things that we're interested in is the effort that those steps take. And we've already seen some examples of things like decomposition into tensor products. That involves generally lots of singular value decompositions, which are actually quite expensive. So in some of the work we've done, the effort on the classical computer to do those things in the salmon boxes actually take longer than the classical solver we trying to replace. And that's even before we get onto the quantum computer. Now that's one of the challenges with the algorithms, and we've done a lot to reduce that. And Christoph's talked about circuit depth and then the impact on running on the quantum computer. And to some extent, those are tradable things. We can reduce the effort on the classical computer and increase it on the quantum computer. So let me then move on a little bit more specific. I keep pressing the wrong button. So this is some actual work, and again, I've sort of done a repeat of that diagram on the left, and we've done a lot of work where, because it's all linear, there is a whole sort of edifice of classical linear algebra that we can draw on to analyze what we're doing. So this is actually the HHL algorithm, which is basically, we make the system Hermitian, solve it as an Hermitian system. All the eigenvalues are orthogonal to each other, and we're just doing straight linear algebra within a quantum context. And we do this in emulation. All of the work that we've done is emulation. We are totally focused on error-corrected algorithms. None of the work that we've done is NISQ-based. And if you look at the figure on the right there, don't worry about the labels. The black line, this is convergence. This is our error. So this is a measure of how the error reduces with each outer loop that we run. So we start with an error of sub 10 to the minus 2. We run the solver and we reduce that to 10 to the minus 12. And the black line is what the classical algorithm does, no quantum whatsoever. And then there's 3 quantum lines, one of which is the green line, which more or less matches, in fact, essentially is the same as the black line. We've got the purple line, which follows the classical line for a little bit and then stagnates. And then the blue line, which effectively is slowly diverging, and at some point will go bang. Now the numbers, the legends, I'm not going to explain what they are, but they are different settings on the quantum solver. Effectively, they're the number of qubits you use. So you can get it right, you can get it wrong, but it's still usable, or you can get it completely wrong. And these are the sort of things that we're trying to learn from the work that we've done. Let me move on. We've talked about the encoding. I'll say a little bit more about the encoding. And I said the bit in bold there, Christoph's already very eloquently explained the complexity versus quantum usefulness. So this is some very recent work that Christoph and I have done, and the paper's just gone up in archive. It's a bit busy, but I'll explain what it is. Preconditioning is something that's very popular in classical computing. So if you're trying to solve a matrix make system A times X equals B, where X and B are vectors, then you can very effectively solve that with preconditioning, where you effectively solve P times A times B equals P equals, so P times A times X equals P times B. That's a well-established technique, but it can be quite expensive to do. And we've investigated two things here. One is doing the multiplication on the quantum system. So if you look at the circuit on the bottom left, the first half of that circuit, we are loading A, and this is a very simple circuit. It's not relative to the picture above. And then we are then, the second part of the circuit then is loading P, and that circuit will multiply A and P to then load A times P. Now, on the picture above is the condition number with different levels of what's called infill. So when we make that approximation of the sparse matrix if you just directly invert a sparse matrix, you get a very dense matrix. So the numbers in brackets 0, 1, 2, 3 are increasing levels of what's called infill. So we get a better approximation of the inverse. I'm not going to go into the details of why this happens, but effectively you get the opposite. The opposite happens to what we would expect classically. So, as we try and make a better approximation to the inverse, the condition number goes up, whereas classically it should go down. On the right-hand side, we now do the multiplication on the classical computer and then encode P times A, and you then get the behavior that you'd expect. You get the behavior that matches the classical computer. So as you do more infill, your condition number goes down. And I'll just go back to this picture. So what that is showing is this thing that I talked about. Doing that preconditioning on the classical computer is very expensive. Working out P times A on the classical computer is very expensive, but you get a shorter quantum circuit or better quantum circuit, whereas encoding A and P separately is cheap on the classical computer, but performs badly on the quantum computer. And these practical implications of using the quantum computer to solve linear systems are the things that we're interested in. And then just finally, as people have been talking, I've just added this one in because both David and Christoph have referenced this. If you've got a matrix that's a sparse matrix, say you've got an n by n matrix, let's say you have 5 diagonals, the number of non-zeros in that is typically 5 times n, where n is a big number, not always. But you can make certain approximations, and David mentioned you can make sort of approximations of smoothness. You get lots of values that are almost the same, but not quite, and so you can smooth those. So on the very left, there is a smoothing parameter. The more smoothing you do, then the number of unique gates. So essentially, everything's a rotation angle. If you can make rotation angles all the same under certain circumstances, you can coalesce them and turn one rotation into pair up rotations and convert 2 to 1 and repeat that. So we've got different levels of infill. Single level of infill here, different matrix sizes that we're smoothing. And as you can see, the larger the matrix, then the more opportunities there is for reducing the number of equal valued rotations, which is on the left. So you can see, the bottom green point, you've basically got a factor of 100 reduction in the number of unique entries. But when we come to convert that into rotation gates, then that becomes a factor of 15-ish. So you can't go straight from reduced angles, reduced values of angles to a reduced circuit. But nevertheless, it's a reduction. And what the final figure is the level of accuracy that you get from your solution. So just setting a smoothing factor doesn't necessarily guarantee the level of accuracy you get. And you can see if you want to target a sort of 1% accuracy in your actual output, your smoothing factor gets smaller and smaller as the matrix rises. But there is a benefit. You go from something like, just look at it, say 70% to 40% to 20%. So you are getting a sublinear benefit from the smoothing. And that is it. I was just going to leave you with this thought, something that occurred to me, of applications of what emerged from the collision of algorithms and data, and practical applications of what emerged from when practical data is used. So I say that because often algorithms and applications often get bundled together in a sentence as if they're the same thing. They're not. We've done a lot. We've all done a lot in the work package. We've done a lot on the applications and bringing together. So it's been a really nice project, bringing together applications, algorithms, and had a lot of fun. So I'll stop there.
Thank you very much, Leigh. We are calling now everyone to the stage, the virtual stage. Perfect. Thanks, everyone. Very cool talks. I think a good mix between understanding the project, understanding the technical part of how everything was done. So there are several questions. I don't know if you had the time to read it. So I'm going to go a little bit more in order, and then kind of the generals I will ask to all of you. So for Mark, which decoder was used for those memory experiments? You're muted.
Sorry, you can hear me now.
Yeah.
Yeah, it would have been minimum weight perfect matching was the main decoder. I know Riverlane developed a few alternatives and they might have been considered as well, but the bulk would have been minimum weight perfect matching, the most usually considered one within error correction codes.
Thank you. Next question for you, Mark. Could you explain how your approach to quantum error correction or error resistance addresses the scalability and reliability challenges in quantum computing?
Yeah, they're very linked, scalability and error correction, in that we need scalability on the hardware. We need to reach really large numbers of qubits, but it's the quantum error correction that allows us to effectively use such a large number of qubits. If you just had 1 million qubits, let's say, but no error correction protocol, then they wouldn't necessarily be providing an advantage. So it's that combination, many qubits and quantum error correction, that allows you to tackle the sorts of problems that we're talking about today, but also many other problems as well.
Thank you. Then we have, I think people really love the paper that you did in the past about the shuttle and high fidelity paper for Mark, and people love the analogy that you use, Christoph, in your talk. Now we move on with Christoph. A question for you. Your simplification of the data loading is very interesting. Can you share more info on how this pursuit of reducing required gates is going?
Yeah, sure. So in general, if you have a matrix with a lot of structure, regardless of what kind of structure this is, I think then you will be able to find a more efficient circuit. But if you have a structure where you don't have that many repetitions, but only like a few repetitions of the values, then it will be much harder to find an efficient circuit, and you will need many more gates just to load all of these different values onto the quantum computer. I think an alternative strategy would also be to approximate the matrix by something similar, which maybe has more identical values, or which can somehow be cast analytically or factorized in some way. But yeah, I would say it's still an ongoing topic of research.
Awesome, thank you. Now we move with David. With these tensor network state approximation approaches, do we have? Oh, thank you. Can you read it?
Yes.
Awesome.
I wish I could say I knew for sure, but I don't. But I suppose we do know for tensor networks that the bond dimension is sort of a proxy for the entanglement. So if we can generally expect, I guess in the case of any sort of matrix product state case, that if we're looking at a high complexity but low entanglement state for just generic data, then we don't have to do that many layers, for example, of C. Duran's work. We don't have to do as many layers for that. In the case of the answer state preparation, I wouldn't know. I think it's very heuristic, so I couldn't really tell you.
Okay, thanks. One question for Leigh. What happens to the green line if more than 20 iterations are done?
I saw that one. So these are emulations of quantum devices on a classical computer. So the emulator has a precision. The emulator all goes in double precision. So both will just hit the double precision limit in that case. And a lot of what we're doing is assuming a perfect computer and perfect gates to fully characterize and understand the algorithms. You know, we're looking forward to ever corrected devices and being able to run these things on an actual device and then see what happens.
Actually, it's asking if you have any paper preprints for all these results.
Yes, they're all. I saw that too. They're all out there. If you just search for me on Google Scholar.
Feel free to put it in the chat as well, Leigh.
Yeah. Okay. I'll do that. Yep.
Awesome. Another question for Christoph. If you have the block encoding for some matrices, can you get the block encoding for the product sum between the matrices?
The answer is yes. Block encodings are very cool and a very useful tool. You can, if you have matrices block encoded, you can sum them, you can multiply them with each other. There's some difficulties about normalization factors that get worse, so you have to keep that in mind. And the recent paper that he just mentioned also has a small improvement there. And you can also do other operations with block encodings. You can apply polynomial functions to block encodings. That's how you can do a lot of different things with block encodings and unify most known quantum algorithms actually in this language.
Thank you. There are some kind of general questions that this is just like, feel free to answer if you want to, all of you. But we have a question: when do you estimate a fully functional quantum computer will be realized? The 400 million question. Who wants to bet?
Well, I can contribute. I know it's a famous answer for technology that's in the future with unknown incoming date, but for us at Universal Quantum, 5 to 10 years with the hardware projection in terms of the various generations of our hardware in that 5 to 10 year range, we should be reaching qubit numbers that we can do full-blown error correction and niche applications. It might not be computational fluid dynamics, but issues such as quantum chemistry seem more achievable.
Awesome. I think that was a great answer. Another question that I like a lot. I lost it now. It was for you, Mark, as well. Somebody was asking what are the differences between your platform and the Majorana chip that we heard recently.
Yeah. So the question is like, is there synergy between using different quantum computers in the future? It's an interesting one. There's definitely different strengths and weaknesses between hardware platforms. Trapped ions are famous for their fidelity. Universal Quantum now putting forward the scalability piece. Operation rates on superconducting are clearly more performant in terms of speed than, say, trapped ions. So there's different strengths and weaknesses. But it really will come down to this question of what hardware platform can reach the sufficient scale. Both superconducting and trapped ions will need to reach hundreds of thousands or more qubits to run fully blown quantum error correction protocols. And there are key blockers for scaling, and they're different for each technology. Each technology has their own challenge. So I see this journey going forward that one or a small selection of the hardware platforms will be able to tackle those scaling challenges and reach the large scale. And that's when the strengths and weaknesses question will come back to it if there's more than one.
Great answer. I think I'm just gonna let me just check if there's anything in the chat. Thanks, Leigh, for putting all those links. I think I'm gonna finish with the question from Frank. How you think that we can approach these in other regions like Africa? Any thoughts on that?
All I would say is government investment. The government investment has transformed what we're doing in the UK. So lobby your government with my answer.
Very hard.
Research. I mean, we wouldn't be doing what we're doing if we weren't getting grants from the government to do so.
Thank you. And answering the question, yes, the presentation is going to be available because the recording is going to be available on social media on the website that I put before, the QEC Project website. So I think with that, we close. I think it has been really, really good. We had really a lot of people. So thanks, everyone. Thanks to the speakers. Thanks to everyone joining us today. And thank you, all of you and all your teams for working on this project for 3 years. Thank you. Have a good day.
Right.
Cheers.